So in the first half, actually first three items is more about the Maxwell equation. We will have a bit modification to the Ampere's law, which we have learned in chapter 29. And we'll add an additional term to make it complete. And in this textbook, it's called Ampere-Maxwell law, rather than the Ampere's law. And based on that, we'll talk about the displacement current and roughly talk about the Gauss law for magnetic field, but actually it's even more simpler than the Gauss law for electric fields. And the second half of this chapter is some sort of hardcore physics. Actually, you can regard it as a story to listen. I cannot probably I will not ask a question about that because it's too hardcore to ask you questions. Yeah, so for this one, Gauss law for magnetic field, and actually you have learned Gauss law for electric field in chapter 23. So we have the electric flux equals to the enclosed charge over the epsilon naught. But for magnetic field, we don't have magnetic monopole. So in that case, we don't have a corresponding term to the enclosed charge. We don't have enclosed monopole. So in that case, we always have positive and negative for the so to make it a dipole, a complete dipole. Even you break a magnetic state, it will become NS, something like that. So on the right side, we only have 0. So it makes the Gauss law for magnetic field to be simpler. So in that case, this magnetic field for an example. As an example, so even for surface 1, surface 2, if you just integrate all the B dot dA over the Gaussian surface, the answer will be 0 as long as the surface is closed. So it's nothing special. So the next one, we talk about the induced magnetic field. So it mentioned that a changing electric flux induces a magnetic field B, and this is called the Maxwell's law. So actually, in my opinion, I think it's quite strange to separate the Ampere's law and Maxwell's law, but it is a way of presentation in this textbook, so I just follow it. And in that case, yeah, on the left-hand side, it is the line integral, the B view for a Ampere's loop. So in chapter 29, we know that ES is somehow like I. Mu 0 is on this side or less. I'm not really sure. B dot ds. I'm not really check it here. Mu 0 I. Yeah, should be mu 0 I or I enclosed. Something like that. So actually for this one, it is a DC current or fixed current. And in that case, here in that term is like mu 0 epsilon naught d phi e dt. So in that case, we have mu0 here, mu0 here, multiplied by a current. So it is somehow like this term is also a current. But actually this, yeah, you can regard it as a current. But here we see it in a magnetic field way. So for example, here, suppose this is a capacitor, and there is a current charging this capacitor. And from the beginning, there are no charge on both of the plate, and then as long as there are some current, the accumulated charge start to increase. So the E field between these two plates are also increasing, which means that the electric flux for maybe this surface is also changing. So as long as the electric flux is changing, so this term is not zero. This term is not zero. It feels like there are some current going through it. But as long as you have learned the circuit analysis, you know that if the current is DC, then it will start to increase, and then the voltage will start to increase, and then will exponentially stop, something like that. So for DC, suppose you learn in high school, you learn that the DC current cannot go through the capacitor, but if this current is a sinusoidal, then you'll see that the sinusoidal can go through, because it's just like this part is going up and down. So this part so this current is going up or down, up and down, and this side will also follow, so that it feels like the AC current can go through the capacitor, and as long as it is a DC AC current, then the E field between these two plates also keep changing, and this term won't be zero. For most of the time, except some specific moment like here. But most of the time, this term is not zero. In this case, it feels like there are some current going through this plate, but actually there are no charge going from this side to that side. And this one tells you that as long as there are some E field changing going into the page, so you can imagine this one is a circle capacitor, circle plate capacitor, and so this is a cross section. So for this Ampere's loop, as long as the E field is changing, then it will generate the induced magnetic field like this. So it also obeys the right-hand rule. So for the B field, use the right-hand rule, follow the direction of B field, and then the E field going inside. So here it mentioned that, as an example, this sort of induction, we consider the charge of parallel plate with the circular plate. The charge on a capacitor is being increased at steady state by a constant current I in the conducting wire. Then the electric field magnitude between the plate must also be increasing at a steady state. So here it mentioned the case that I keeping to be a constant. So the charge here increase linearly. So in this case, this term is a constant, maybe larger or smaller than zero, but not equal to zero, but a constant term. and in that case, there will be a fixed B field, and actually the B field will be perpendicular to the changing direction of the E field. In that case, as long as the E field is increasing linearly, so the B field is perpendicular to it, like this. So the electric field is direct into the page. Consider circle loop point one. Where's point one? Point one is here. Point one is here. So a loop that is concentric with the capacitor plate and has a radius smaller than that of the plate. So we imagine this is the Ampere's loop, and this is the radius. This is the radius of the capacitor. So within this capacitor, and then choose an Ampere's loop which is concentric, 同心的 Ampere's loop with this capacitor. Then you can see that because the electric field through the loop is changing, the electric flux through the loop must also be changing, because it's just because you can imagine E is uniform, so the integration of, so actually phi E, you know that phi E is actually nothing but this one, E dot dA, like that. So actually this is not a closed surface, so we don't have a circle here. So this electric flux is like this. So as long as E is constant, and then it is uniform over the surface, and then as long as this is uniform over the surface, so that this integration is somehow like E times A. So as long as E is increasing, this term is also increasing, and we take the derivative. So E is somehow like maybe K times T. So we take the derivative of time, it turns out to be dt. So it will become K, and then yeah. So only this term to take the root, and of course this one is another term. So we have A here, somehow like that. So according to the above equation, this changing electric flux induces a magnetic field around the loop. So the magnetic field is like that. So this is called the Maxwell's law, and this is the Faraday's law. This is the Faraday's law. So they are a pair. So in this case, the changing E field will generate the induced B field, and the changing B field or changing magnetic flux will generate the electric flux, somehow like that. And here there is a negative sign, so there's a negative sign. And actually, it means that for this one, for the Maxwell's law, we don't have the negative sign. This is positive. This is positive. So it strongly follow the right-hand rule. Actually, both of them follow right-hand rule, but this is more straightforward because you can only consider, you use the right-hand rule, follow the B field, and then this is the E field direction. But actually, this one has a negative sign. So if you use the right hand to follow the E field, so this is a negative direction. So the B field point to that way. So in that case, the negative sign for the Faraday's law means the induced E field is counterclockwise. counterclockwise. If the magnetic field direct into the page and is increasing. So this is the point for the negative sign here. And this is very important. Can't be both of them are positive, then yeah, you'll see that later in the next chapter. This negative side is quite important to make how the EM wave generate. So actually in chapter 29, we have the Ampere's law, and here we have Maxwell's law. Here we have Maxwell's law. So this one you talk about the I is a constant, or I is constant. And here we talk about the E field is changing. The E field is changing. So we still need to determine when to use which one. When to use which one. So in that case, why not make them together? So we try to add the right sign together. So this is called the Ampere-Maxwell law. So it's just like a few years ago, you should have listened to the song called PPAP. So we have Ampere's law and Maxwell's law, and then we combine them together to become Ampere-Maxwell's law. So in this case, when there is a current but no change in electric flux, and this means that only the first term is non-zero, the second term will be zero, so it will reduce to Ampere's law. And when there is changing E field but no current, then the second term will be non-zero and the first term will be zero. So it will reduce to Maxwell's law. So in that case, we try to write both terms together, and then we try to determine which one is zero, which one is non-zero. And then we can determine on the right side whether it is positive or negative, and determine the direction of the B field. Okay, so there is an example. So a parallel plate with circular plate of radius r is being charged. Derive an expression for the magnetic field at radius r for the case r is smaller or less than capital R. So actually, this is the plate we see before, and this is the cross section of it. So we need to use the Maxwell's law. Maxwell's law, because it is actually that case. So we have integration b dot ds equals to mu naught epsilon naught d phi e dt. So as long as we can imagine the B field is uniform over this contour, so B dot ds can be reduced to 2 pi r B. And I need to remember of you that when you use maybe Gauss law, Ampere's law, Faraday's law, if the problem does not specify the Gaussian surface or the Amperean loop, then you should draw it out. You should specify what kind of Gauss law you are using. You cannot just say, according to the Gauss law, but it doesn't mention what kind of Gauss law you are defining, then actually there are infinite many ways to define, and probably most of them are meaningless. You cannot come up with some trivial answer, and as long as you need to choose the correct Gauss law to have a meaningful conclusion. So that's quite important. It's quite important. And so actually, this is mu. So this is mu naught epsilon naught, and just now I already mentioned that phi e is this one. This is nothing but e times a. So we substitute e times a here. And actually mu 0 epsilon naught. And a should be a constant. A shouldn't change. So we can just factor a out. And actually a is nothing but pi r squared, because we only consider the area here. So it is like mu 0 epsilon 0 pi r squared dE dt. So pi and pi can be cancelled. One of the r can also be cancelled. And it turns out to be b equals to mu naught epsilon naught r over 2, and then dE dt. So it looks like a formula which is quite neat. So for the next question, evaluate the field magnitude B for R equals to capital R over 5, and dE dt equals to 1.5 times 10 to 12 volt per meter second. So actually we only need to substitute all the numbers. So mu naught epsilon naught R over 2 dE dt, and yeah, we want to have mu naught is 4 pi times 10 to minus 7, and then epsilon naught is 8.85 times 10 to minus 12. R is 11 millimeter. 11 millimeter. So over 2 and then multiply by 1.5 times 10 to 12. So this one is here. So in this case, it is 9.18. 9.18 times 10 to minus 8 Tesla. So it is quite more magnetic field. So for part C, derive an expression for the magnetic field at radius r for the case r is larger than capital R. So we consider the Ampere's loop outside. So similarly, we use the Maxwell's law, mu naught epsilon naught d phi e dt So for the left side, it is the same 2 pi r. So this is r and b. And for the right side, mu 0 epsilon 0 a is still pi capital R squared because there are no E field changing outside. So for the area, it is pi R squared rather than small r. So dE dt, because there are no E field. So in this case, we have B to be 2R mu naught epsilon naught R squared dE dt. Like this. Okay. Any questions? Okay, so we talk about this. Just now I already mentioned that for Ampere's law itself, the right side is mu naught I. And for this one, this is mu naught epsilon naught d phi e dt. So usually in physics, we can consider the dimension of the formula to check whether it's correct. As long as both of them are correct, which means that the dimension of this term and this term should be the same. Which means that this one should be some sort of a current, And in that case, we'll call it the displacement current. 位移电流. So if you compare the two terms on the right side of the equation, Ampere-Maxwell law, you see that the product epsilon naught d phi e dt must have a dimension of a current. In fact, that product has been treated as being a fictitious current called the displacement current, ID. So you can have some ramification like this. So ID is epsilon naught d phi e dt. And suppose it is a parallel plate capacitor, so we can assume the E field is uniform. So similarly, we can write epsilon naught a dE dt and then we try to multiply it by d and then divide it by d so that nothing happens. And then in this case, we can see that epsilon naught a d, this one is what? This one. Do you remember what is it? This is a capacitor, right? This is a capacitor of parallel plate. Capacitance of a parallel plate capacitor. And this one, E times D is the voltage, dt. So this becomes d c dV dt. So this is what you have learned in circuit analysis. So you can regard this displacement current is the current of a capacitor. Current of a capacitor is somehow similar. So if you just replace this term to be ID, so Ampere-Maxwell law can be written like this: mu0 I enclosed plus ID enclosed. D denote the displacement current. It's a displacement current. So here we further talk about the displacement current, and actually this is similar to what we have derived in chapter 29, but now only for the case that we replace the I by ID from a normal current to be a displacement current. So at that time, suppose there's a constant current charging the capacitor. Not that. For that case, not a capacitor. There's only a wire. There's only a wire. For that one, for chapter 29, we only consider a current I, and then there will be magnetic field circular to the wire, And as long as if the wire has a thickness, so we will consider the B field inside and outside the wire will be different. For inside the wire, it should be like R over R squared. And for outside the wire, it will be somehow like mu0 I 2 over 2 pi r. And this is the same case for the capacitor case. We just use this is a wire, and then we have a capacitor here. We just have a capacitor here, and then we consider the B field generated between the parallel plate. In that case, we consider the B field generated by this wire. And the derivation is actually the same as what I have derived in chapter 29. I just replace I by ID. So I do not repeat it again. So for this one, sample problem 32.2. And so a circular parallel plate capacitor is being charged with a current I. And between the parallel plate, what is the magnetic magnitude of this term in terms of mu0 I at the radius R over R equals capital R over 5. Circular parallel plate is being charged. Okay, so so actually this is the maybe ID, and we can use enclosed. So as long as we have defined the displacement current, the right side will look more simple, look simpler. It's just like we have I enclosed or ID enclosed, but actually you should remember that for displacement current, it should be that term epsilon naught times d phi e dt. And I d enclosed inside the capacitor over ID should have the same ratio as the area. It should be somehow like this. So this is ID. So ID should be something like J times pi R square, pi capital R square. And this one ID enclosed should be J times pi R square. And J and J can be cancelled, so it turns out to be R square over capital R square. So in that case, this one should be mu0 ID R square over capital R square. And R is capital R over 5, capital R over 5 square. So it turns out to be mu0 ID over 25. Or actually, I can just use I here, so I don't need to modify the original one. So I can just put I here, or I can just put I here. Yeah, that's not a great point. So I can just use either I or ID. It's fine. So for part B, in terms of the maximum induced magnetic field, what is the magnitude of the magnetic field at R over capital R over 5 inside the capacitor? So as long as we know that inside the maximum point should be for small r equals to capital R, because this point is linear increasing, and for this part it is decreasing. So for the maximum point, it should be the intersection point, because it is somehow like it should be somehow like this is capital R, and the B is linear increasing, and then start to decrease. So this point should be the maximum point. Which means that B R over 5, B R over 5, B max should be B R over 5, B R, and this is actually mu0 I D over 2 pi R square times R over 5, which is a small r, and then for this one, mu0 I D 2 pi R square times R. So actually, most of them are cancelled. So it turns out to be 1/5, which means that BR is actually 1/5 of the B max. So in summary, we have learned all the Maxwell, all the equation, all the laws for the Maxwell equation. So we have Maxwell's law for electricity, Maxwell's law for magnetism, Faraday's law, Ampere's law. And yeah, actually, why it's called Maxwell equation? Actually, Maxwell summarized this equation into a group so that we can generally use these four laws to solve different kinds of problem. And actually, there are even more equations at that time, maybe like 150 years ago. And actually, so the contribution of the Maxwell is one of it is he add this term here, and then he tried to claim that these four equation combined together they can solve almost all the problem.